Good afternoon. This is Jennifer Beliveau, the Director of Sales from Applied Math Modeling and today's moderator. Thank you for your interest in CoolSim software. We're excited to share with you another great case study using CoolSim software, improving the energy efficiency of existing data centers. With me online today is Paul Bemis and Liz Marshall, Applied Math Modeling's President and CEO and Director of Technical Services. Before we get started, we'd like to inform you that we will have a question and answer session at the end of today's presentation, as we have in previous presentations, and you can enter your questions in the question panel located on the right-hand side of your screen throughout the presentation. If you're having any technical difficulties whatsoever, please click on the raised hand icon and we'll respond to you through the chat window. Without further delay, let's get started. Paul?
Thanks, Jan, and welcome everyone to the presentation. Hello, Liz. I guess you are with me here?
Hi, Paul. I'm here.
Good. What we're going to do today is we're going to take a look at some key parameters that are related to data center efficiency. And I'm going to begin the presentation by just reviewing them. I have reviewed them before in these presentations. I try to do it each time. So those of you who have seen them before, please just bear with me and I'll get through these fairly quickly and then we can move on to kind of the key parameters and what are they. So the first one I'm going to review is power utilization effectiveness, or PUE. It is the total facility energy divided by the IT energy. It is really how effectively is the power that's coming in to drive my IT equipment handling the environment. How well is it cooling my equipment, and how efficient am I being with it? It is made up of everything. Total facility energy is made up of everything, including the IT equipment, but really has an awful lot of components in it, PDUs, UPSs, transformers, etc. But for the most part, and by the way, DCIE is just the opposite of that. And DCIE is the inverse, so good values for PUE are 1.8 to 1.2, and for DCIE it's a percentage really going for 100%. So you can see here that we're up around, an excellent data center up around 1.2, or down around 1.2, excellent DCIE up around 85%. But what's going on with PUE is because it's total facility power in the numerator, the dominant characteristic of that numerator, besides the IT equipment, is crack, chiller, heat pump. And we've seen this a number of times, Liz, where it's really all about this stuff. The other components are modest in comparison. The other components can really, for the most part, be ignored. And that's because if you look at what's here for a list, lighting is nominal. I mean, people are turning the lights out, or they're using LEDs or fluorescents, but LEDs. PDUs have become much more efficient than they were in the past, so PDUs are getting better. UPSs are getting better with efficiency. So you're really left with this group over here of chillers, cracks, humidifiers, the change from latent heat, the energy related to latent heat. And so if you look at that numerator, it's really the IT energy plus cooling energy. If we look at the dominant parameters, cooling energy really is the dominant parameter of the overall environment with respect to PUE. It's the dominant one. So what we tend to do in these webinars is we focus on cooling efficiency. And understanding how these systems are being cooled is key to having an efficient operation. So let's take a look at cooling system energy. They are heat pumps, and they use mechanical shaft power provided by an electric motor to pump the heat, move it from one place to another. They're generally, their efficiency, I like to use coefficient of performance. There are other methods that people use besides COP to measure the efficiency of these devices. Oftentimes you'll see them measured in chiller efficiency, which is actually a kilowatts per ton ratio, but it's got dimensions on it. It's kilowatts per ton. The nice thing about COP is it's dimensionless. We're looking at the amount of heat being pumped compared to the energy required to cool the data center. And here as well, we tend to look at it as COP for the room. Right, Liz? It's not just the chiller that we're concerned about. It's the COP for the room.
It's a more conservative way. It's a more conservative approach of estimating the COP.
Correct. Because oftentimes the efficiency you see just for the chiller is optimal condition, right? The chiller efficiency provided by the manufacturer is going to be, this is what this device can perform under these conditions.
Yeah, at certain set points or within a certain operating range, right?
That's correct, in its design center. And what you and I find is that these are often running way outside their design center. So even though I have a COP listed here that ranges from 2 to 5, oftentimes we see them far below that.
Right. That's right.
But COP is a good one because it's dimensionless. It's looking at how efficient am I pumping the heat out of the room. And the other thing about it is it's fairly easy to get your hands around it in terms of a measurement. It does depend on the configuration, but fairly easy to get your hands around this one. And I would encourage those of you involved with data centers, and if you have a data center, find out what this number is. Now, if you've got DX-based units, they're, direct expansion-based units, and the power to them is specific, therefore, to the room you're in, the data center you're in, the easiest thing to do is to put a current probe around the lines leading to the DX units and get a read on them. That's the best way to do it in a DX case, and fairly easy to do. Liz, I was involved with the data center here, state of New Hampshire, recently, and you remember that's how we did that one. We had the electrician come in, and he just took a current probe and wrapped it around the leads. It's not disruptive. It doesn't cause any issue. You can do it while the machine's running, and you measure the current going to them on the 3 phases, and then you use standard equations to determine the amount of energy consumed, which is the average of the current going to the device times square root of 3 times the voltage. So it's fairly straightforward to measure. Now, it is an instantaneous point in time, and COP is not a constant. It does vary with time. So as the external temperature of the environment changes, so won't the COP. It'll change with time. It'll change with whether the compressor is on or off. The compressor's on always on full time. So I think we all need to understand that it is an instantaneous point that we're looking at, and that the best way to find the COP is to measure power consumption over time and have a plot of it. But we have to start somewhere. And if you're trying to get your hands around how efficient is this heat rejection system working for your data center, the first step is to take an instantaneous read by putting a current probe around these devices and understanding what the numbers look like. I think you'll find them quite revealing. Certainly I have. Now, if it's a chilled water system and the water coming to your data center is also going to other parts of the building or the data center, things become a little more challenging, right? Because you have to know how much, in this case, we're not looking at pure wattage because the energy is being effectively distributed throughout the building or to other data centers. But I would still encourage you to measure the amount of energy going to the chiller and use some method of proportion. You can do it based on heat loads, for example. So if you have chiller that's serving 2 data centers, and you've got one operating at 500 kW and the other one operating at 100 kW, you could do a proportion, I think, Liz. Wouldn't that be fair?
I think that would be. I think that's all you can start with. Yeah.
That's right.
The best place to start.
So don't be afraid of first-order approximations. First-order approximations get you in the ballpark, if you know what I mean. It gets you to the right stadium. From there, we can begin to refine it and get a closer look at what's going on in the room, understand things a little bit better, see if our numbers make any sense, begin to get our hands around these parameters. And this is the first parameter I wanted to stress today, and the first one that I wanted to just review. Because if you then take a look at PUE and instead of chiller energy, you substitute in IT energy over COP, which is really what it turns into. Now the numerator right up here of IT energy, there's often a little more in there than just IT energy. But if we're looking primarily at a data center that is pumping the heat, the dominant load out of the room, it is the IT energy. Yeah, there's some leakage from PDUs, there's some leakage from other devices, but these are the two dominant characteristics. And so that equation falls right into 1 over COP plus 1. So let's say, and this feels right, Liz, if you know what I mean. For example, if we assume our COP is 4, which is a pretty good one, then our PUE is going to be 1.25, right?
Yep.
So, in fact, if our COP is 5, which is a very good number for COP compared to the plot or the charts that I was showing you earlier, remember the range was 3 to 5. If my number's 5, then my PUE is going to be 1.2, which I defined earlier as being excellent. Right? It means that we're using about 20% more energy than is driving the IT equipment to drive the cooling system, right?
Because the cooling efficient is efficient.
Yep, that's correct. Very
it's
efficient.
Working well.
Yes.
It's working well because it's measured by the COP.
Yes. So I know that there's a lot of discussion in the industry right now about PUE and how to measure PUE and what the components are that go into PUE. And people do manipulate this relationship to their advantage sometimes, okay, to make it look good. But I would encourage you to start here. Start with just measuring the power going to your cooling system compared to the IT load in the room, and then use that as a primary metric to get COP and see what this number looks like. Now, oftentimes you can get this information right at your transfer switch, which is what I'm talking about down here. Clearly you have the IT load because the IT load is what's going to be switched out to the diesel generator in the case of a failure of power. So you've got the IT load there. You can also typically find a switch over for the cooling system as well to back up because you're going to have to drive the cooling system in a failure mode anyway, in addition. So oftentimes you can get a read on these things right at the ATS switch. If not, go to the panels that drive them. Again, in the case of DX units, it's easier because the panels typically in the room or near the room in a specific to the room. In the case of chilled water that is shared, that's a little more difficult. The only other thing, Liz, I thought I'd mention here is in the case where it is chilled water, be sure to include the fans in the room, right?
Yeah.
A lot of people seem to leave that out of their COP number.
Well, they do give off a little bit of heat.
They do.
Again, it's not much, but they do give off a little.
As a percentage, it's not much, but it depends on quantity, doesn't it? Because if you've got 5 or 6 craws in the room, and each one of them's got, you know, a 5 kW or a 10 kW fan in it, they add up.
It can add up. Yep.
That's right. So oftentimes the chiller efficiency you get from the manufacturer does not include fans. And what we're talking here about is the efficiency in the data center, the efficiency of the room. How well is it cooling? And therefore, the COP should include fan energy. Yep. Now, the other key parameter here is that the coefficient of performance of a heat pump is correlated to the cold air supply temperature. And you often see plots like this, where you see the coefficient of performance against the leaving chilled water temperature from the chiller. And all things being equal, which of course they're not, but all other parameters being equal for a moment, as you increase the leaving chilled water temperature, or another way to look at this is supply air temperature coming out of a DX unit, as you increase the cold air supply temperature, the coefficient of performance improves pretty linearly. It's fairly flat at a ratio of around 3.5% for every 1.8 degree. That's not my number. That's from Ashray's book. For example, best practices for datacom facility energy efficiency lists that same relationship. Now, there's more to it than this, and you can't use this everywhere, but it gives you a feel. Roughly 10 degrees is going to give you 20%, is just about what that's going to do. The point here is, go ahead.
I was just going to say, I think that it's the ratio here that's more important than the absolute numbers here, because the COPs shown are pretty high, and they're idealized conditions here. So I think that those may not be able to be realized in an actual data center.
That's true.
Probably a device chart for a particular device operating where it's supposed to be operating, but. But the ratio and the range, the ratio, the slope is really the trend is what you can carry forward to other temperatures.
And the point, of course, is get your cold air supply temps up as high as you can. You'll reduce your energy consumption. You'll extend the life of your devices by requiring less maintenance on the machines because they're working less than they would be. And I thought I would just put these diagrams in here, Liz, just to illustrate why that's true. And you can look at them either way. Some people like to look at sort of a block diagram, schematic of what's going on, and others like to look at sort of the enthalpy diagrams. But the point is that in this refrigeration cycle of compress, condense, expand, evaporate, etc., this cycle that goes on all heat pump-based systems, whether it's a DX unit or a chiller unit or your refrigerator in your kitchen, it doesn't matter. They all work the same. Where the energy required to pump the heat comes from is this work right here between 1 and 2. It is pressure that you're increasing. You increase pressure, it increases temperature due to ideal gas law. And it's this work that's going in. They call this lift. It's the delta P between the evaporator and the condenser that actually constitutes the work, called compressor lift. And there's a lot of work going on right now on the idea of very low lift kinds of systems to improve energy efficiency of building. So chillers with very small temperature lift or pressure lift for efficient building design. And the idea is, of course, that you need to get the temperature up high enough so you can dump it to the atmosphere. You need a fairly good delta T across this condenser between the condenser and the environment to get this heat transfer to take place. So you need to pump it up high enough to get it out to the environment, and of course that's where the environment comes into play with respect to coefficient performance, because in the summertime it's going to be lower than it is in the wintertime. But all things being equal, again, the idea behind reducing the lift means that you'll have less work put in, and one way to certainly do that is to bring this temperature on point 1 up. Just drive these numbers up, and that's leaving air temperature, supply air temp, or leaving chilled water temp. If you can get this point 1 to come up, point 1 and 4 really, to both move up, then you reduce the amount of area here and therefore the work. So, okay. So how does this apply to data centers? Well, the efficiency in a data center is correlated to maximizing delta T's across the heat exchangers. Again, what we're trying to do is get good heat transfer. We need to increase the hot air to return as high as we can. We need to increase the cold ice supply temp as high as possible while maintaining ASHRAE inlet temperature guides. And that's where CFD comes in, is being able to model those relationships. So just a quick review of the heat transfer relationship. It is heat transfer is mass flow rate times specific heat times delta T. And each device, whether it's a CRAC or a CRAE, uses this. They have a fan coil system. They're transferring heat from the data center, so you want the return temps to be as high as you possibly can. And you're trying to, the delta T here is actually driving. This is the forcing function. This is what drives it, along with mass flow rate. But it's the delta T right here that gives the heat transfer the kick, I would say. Sometimes you see this as difference in potential written in other forms. It's also important to balance the mass flow rates, because the same relationship applies to the IT equipment itself. It is the fans on the back that are pulling the mass flow rate. Specific heat is constant for both for the environment, so that stays constant. And what you have is delta T's. And the typical delta T's that you see for IT equipment are 20 degrees. Now, they've gotten a little higher. Most recently, you see them as well at 30 degrees. But generally, we use a delta T of 20 as a way to get into the park. Okay? So as you begin to look at your cooling system and optimize it, the first thing we recommend you do is take a look at the airflow situation and find out if it's balanced. I think this is probably the single biggest thing. Wouldn't you say, Liz, in terms of getting these rooms right?
Well, it is important, but I'll tell you, you can't just figure it out on the back of an envelope, because if the flow field isn't getting the cold air to where it needs to go, then having a balanced airflow situation is not gonna work for you. It only works if you know from a CFD analysis that you've got the cold air going where it has to go.
It's not sufficient in and of itself, is it?
Right, to just add up the supply air and the demand air. You have to be able to demonstrate. You have to make sure that the supply air goes where it's needed to go. It doesn't short circuit back to the cracks.
Right. Having said that, you can take a look at your IT load, use a rule of thumb of 156 per kW, and see what your demand feels like, what it should be. And then take a look at your cooling units and see what they're blowing, and just look at that ratio. Just to get an idea of what I find is that we're generally got too much air in the room,
way too much air. Yeah, that's the problem. People overdo it with the air.
That's right. And the reason they've overdone it with the air is they built the data center to handle a certain max load of IT capacity.
Right.
And they very rarely run that kind of load.
Right. That's right.
And having N+1 redundancy makes it worse because you're adding yet another unit in the room. So what you try to do is to reduce the airflow supply to match what's needed by the servers. Now, as Liz correctly pointed out, you can only do this to a certain point where you begin to run into trouble getting the air to where it needs to go, and that's where CFD comes in, is where you begin to look at that distribution. And once you've done those two things and you feel fairly good about it, then go to your supply temp and start to move it up. And 80.6 is the floor, the threshold of where those rack inlets should be. And the last point here is use containment to make sure the air gets to the right point. So a couple of metrics that have become quite popular, we're beginning to use them in our output reports and so forth quite a bit, is RTI. RTI is return temperature index. And this is that ratio, Liz, of just really what does the flow rate look like. This is the rack demand compared to the rack supply. That's how we look at it. We do less delta T's here because we're assuming the delta T's are relatively uniform.
About the same, right.
Yeah. But we're really looking at the ratio of these airflows. And you want them to be, near 100%. So it's a measure of balance. And if they're at 100%, then you're giving the room just as much air as it needs, and no more, and that's optimal for energy. But yet, again, of course, you have to make sure it's getting to the right location. If it's greater than 100%, then you've got recirculation going on around the racks. And what we tend to find is that it's often much less than 100%. That's generally what we find. Yep. Now, the other one to look at is the rack cooling index. And there's two metrics here. There's a high and a low. And this is essentially a gauge. It is a measure of compliance to the thermal guidelines set by ASHRAE of the racks in the room. How many of them are exceeding or under temperature. RCI high deals with the ones that are over. RCI low deals with the ones that are under. And it's not only how many, but it's the percentage of how many.
It's how much. It's how much above and below, right?
Yes.
So having temperatures that are very, very cold, for example, will give you a worse reading than having temperatures that are only slightly too cold.
Right.
In other words, if you have 10% of the racks with temperatures that are below the minimum, if those temperatures are way below the minimum, you'll get a worse reading than if those temperatures are just a degree or two below the minimum.
Yep.
And same with the maximum too. So it really accounts for both features of the rack inlet temperature fields.
Right. Fairly good numbers. I'm beginning to like them. I'm beginning to use them quite a bit. First introduced by some of the DCEP training that went on by the DOE. Magnus has been on our show before, and he came up with these quite some time ago. I like them because what it allows you to do is between the RTI and RCI gives you a feel for where you stand in that energy optimization area. The trick is calculating them, but we've now taken care of that for you in CoolSim. So What I thought I'd do here, Liz, is just take a look at a data center. This happens to be one that we have looked at before. So just for those of you in the audience, you've seen this data before. The data center itself is not so important. That's why I used it again. It's the methodology we're using to understand how to optimize this design in this data center. So this one's a fairly small one, 145 kilowatts. It's a natural convective return, and it has an N+1 cooling system. They are DX based. But right off the bat, we've got a high cooling capacity. Now this is often one that people look at this. They say, well, how much cooling do I have as a ratio? But it's really not cooling capacity, is it? It's not so much I can cool this amount of equipment. It is, what flow rates are they running at, for example?
Mm-hmm. Mm-hmm. Yeah, it's a combination of both, really.
Yeah.
Yeah, it's a combination of, yeah, how much excess airflow have you gotten? Yeah, and what does that translate into cooling capacity? How does that translate into cooling capacity?
Yeah. So here's, in this case, the customer, of course, is interested in how can I reduce my total energy consumption? How much is it going to cost me to do that? And the approaches that are optimal for our best is VFDs, because what VFDs do is they allow you to vary the air supply amount, the quantity, the volume, to match the needs of the equipment in the room. And so your cooling system effectively becomes variable. It's a variable device that will go up and down. And that together with containment of some kind, cold or hot, I tend to prefer hot, but either one, are really the things that you look at to improve the overall efficiency in the room. So this one happens to be DH units. These are Liebert DH units. There's 4 of them. And what we always do is first validate the model. So we create a CFD model. It's fairly easy to do these days and fairly reasonable in terms of cost to do it. Then we perform some baseline calculations to make sure that the model is valid. We begin to then look at alternatives. What happens if we shut units down? Now, shutting units down is not a panacea, because once you shut a DX unit down, remember there's a hole there and it's going to leak. Mm-hmm. So you need to be careful of things like backflow, right? Right. Mm-hmm. Having said that, it's better than the alternative, which is leaving them on. Mm-hmm. Generally, a rule of thumb is I'm finding that a DX unit like these will generally run $10,000 to $15,000 a year just to leave it on. So you want to turn them off if you have no choice. A better thing to do would be VFDs, which now you can put on some of the newer DX units. Even on the older DX units, you can take them down about 20%, 30%, and still have them work okay. Mm-hmm. Mm-hmm. So VFDs is still an important thing to look at. And then add some kind of containment, either curtains, which are very cost-effective, or solid containment, or chimneys. There's a variety of things you can do in the containment area. These things pay off quite quickly in terms of return on investment. And then once you've done that, begin to increase the cold air supply temp as much as you can to both reduce the amount of work, energy, to your chilling system, your cooling system, and to increase its life as well, because you'll have to maintain it less, and it will just simply last longer due to less work. Now, the initial model we ran in this case is, you see here that I used the factory specifications for flow rate. Mm-hmm. Mm-hmm. Most typical, right? You mm-hmm. look up, because we use libraries, so you grab mm-hmm. a DH192 and you drag it into the scene, and it's going to have already parameters that include flow rate. So mm-hmm. the specifications called for 12,000 and 15,000 respectively, and you see what happened here on my output. So here I'm trying to validate. When I'm looking at,
so you measured the supply temperature.
That's correct.
And you used those values as boundary conditions.
Exactly correct.
And then use the factory flow rates, right?
That's right. And this is most typically what I do is I will, if it's an existing data center, just put a probe down on the floor and measure the supply temps. It's the quickest way to calibrate or to validate the model and to correlate the model. Put a probe down there and measure it. So you see here my presets equal my measured because I set them to be that. That was a boundary condition.
Mm-hmm. Right.
But what I'm seeing on the return side is I measured or had the customer also measure the returns for each one of those cracks, and here they are in red. And you see here that my predicted, based on my CFD model, came back low. Now, the only reason that they can come back low is that I've got too much flow rate, because you see here in our equation, that's the only variable left besides density.
But you can also imagine excess cold air mixing in the room with the exhaust air, and therefore having a cooler temperature coming back to the cracks, to the crack returns.
So what I did in this case is drop the supply down a little bit. Now, it was clear to me that it wasn't quite running at 54.4 because of the temperatures I was seeing here and what we were predicting. So I dropped it back down a little bit. And yes, there could be some mixing that's going on here that I'm not accounting for, Liz, such as there could be some bypass airflow through the tiles because I didn't turn on tile leakage. There could be cable cutouts I'm not aware of. There could be some underfloor obstructions I'm not aware of. So, but in this case, I didn't have a lot of data to go on because it was a remote situation, and we were just, so the approach I took was to vary those flow rates a little bit. And you see here that the predicted and measured came in quite nicely. So I'm within a degree there on average. And that tells us that the physics, at least of the cooling systems, are running fairly well. Now, the next step, if you wanted to validate even more, would be to go out and make some samples in the room, samples of temperature on the backs of racks or somewhere, and keep tuning the model. Again, it depends on what you're trying to achieve. The tuning of models, I think you and I have learned, can go on long beyond what is reasonable.
Yeah, and it's also a little bit complicated because the cracks emit air, comes up into the room, goes through the racks, and the air that goes back to any one of the cracks is not necessarily the same air that left it. So you've got, you know, the supply air mixing with what's going on, what's coming from other cracks, and then returning to any given crack. So it's not a one-to-one correspondence of the air going out and that being the same air coming back in. So because there's mixing, it's hard to make an adjustment on one crack to try and make it come into line a little bit more. For example, if you look at your crack number 2, you can see that's the one that's probably the furthest off. However, if you made an adjustment if you made a further adjustment to the flow rate on crack 2, it might not make as much of a difference. It will make some difference there, but it might impact the others as well because they're all working together.
That's right.
So yeah, it's a complicated scenario.
Yes, yes. In fact, we know
they're all coupled.
They are coupled. You and I both know that the relationship between flow rate here and predicted temperature over here is related through a very nonlinear relationship, 3D relationship. The other thing that I think here is important to point out is that measurement itself gets problematic because here, one of the things here, Liz, that I've always noted is we measure the return temp on the crack units using whatever the crack unit reports. Well, the crack unit's reporting a single point on the return. It's a probe. Where here, what we predict is we predict an average based on a surface.
That's an average. Yes. Average across the entire crack surface.
Exactly right.
The entire return surface, right?
Exactly right. So we don't know what the profile really looks like. We're merely measuring apples and oranges here. But again, this is all within the realm of getting your hands around the big parameters and trying to understand how to steer the ship in a big ocean. So, right? So getting your hands around some base parameters and understanding, and I mean, I felt fairly good about this because I got my temperatures to line up fairly good. That's all I had to go on at this point. I've had other studies where they've gone around with a balometer and measured flow rate coming out of the tiles. That's a good thing to calibrate. Anything you can do to validate. But
the other thing go ahead.
But at least do the cracks. That's what I was going to say. At least do the cracks.
Well, yeah, but the other thing too is that it's not a stretch to cut back on the flow rates on some of these cracks if they're older.
That's right.
You know, because dust gets in filters and
exactly right.
Things don't work as efficiently. So it's really not.
They're belt drive machines, most of them. They're not direct.
Yeah, so they don't necessarily, work up to the factory specs if they've been, in use for 10 or 20 years.
That's right. That's right. It's not surprising to see a 20 to 30% variance on them. So let's assume that that's okay. And again, let's now take a look at the flow rates of the supply versus return, and you see right away that they're out of balance. So this is the pre-simulation report that comes from CoolSim. Before simulation, I have simply taken the 39.5, which is what we just determined was appropriate for supply, which is a conservative number, considering that it was blowing harder than that according to the factory specs, and we compare it to the demand of 22.5. So we've got far more airflow than we need to satisfy this room. And that's already going to be a problem, and that's your opportunity, first off, for improving or saving the energy in the room. Mm-hmm. So here it is in a simple matrix form, and you see the RTI is 57%, which is the ratio of those two. It again is the required over the supplied, so it's a ratio less than 100. The RCI high is 100%. I've run a simulation here already, and I've looked and done the calculation, and the RCI is 100%, which means none of my racks are out of spec on the hot side.
On the high side, right.
Right, but look at the low side, 44%. And my average supply temperature, 60.75 degrees. So very cold. I mean, ideally, they're running 20 degrees below where they could be running on that supply temp.
Right. Right, right. Colder than they need to be. Not endangering any of the equipment, but perhaps endangering the budget.
That's right.
More than the equipment.
And so the PUE is greater than 2, which means that they're spending as much money pumping the heat out of the room as they are electricity going into the room, which is expensive, just flat out expensive. And if you're a colo or you're in a business where you're being measured on the efficiency of this environment, this is obviously an opportunity for you to do a better job. Okay, so here is the model. Again, we've used this model before, so I'm not going to dwell on it, but it's a typical DX downflow based environment. Standard rack rows. I think the size of this room is only 1,800 square feet. But a couple of things I wanted to show here is just take a look at what's going on the supply side. So here is supply path lines, and you see you can just see a lot of them. And ideally, you should not see any of these at all, right? They should.
Well, they're going back to the cracks.
That's right.
Yeah, they usually get sucked right up by the rack inlets, and you can see a lot of them heading back to the rack returns.
Right. So this is bypass airflow right here. It's coming back, and it's doing two things. It's cooling off the return temps, which is making a very poor delta T across these crack units, and you're spending a lot of money pumping it in the first place. I mean, look over here on this one on the far side of the room. They're just coming right up out of the floor, and it's not going anywhere. It should be, ideally, and you can see a few of them going into, they should come up and go straight into the rack. But here they're coming up and going straight into this crack unit here is not doing much work at all. And if you take a look at our summary report, we can see that. Let's take a look at our delta T's across these units, and we'll find that these should be 20 degrees. You can see this one's 8 degrees. So that's just not very good here, what we're seeing, 9 degrees. This one's not too bad. We're seeing 13 degrees there. They should all be 20, ideally. And you see in the rack cooling report, I mean, it's cold. The inlet temps, let's go back and take a look at our rack inlet temperatures. And remember, the threshold on these should be, the lower threshold, according to the ASHRAE spec, is 80.6. Oops, I'm sorry, 60.4 on the cold side. And you see here that I've got many of them down below that. So I've got some of these running at 57 degrees of temperature. So just from a thermal point of view, not very efficient. So we've got an RTI that's telling us that we've got way too much air. The current DX units don't support VFD, so the only choice you would have is to shut them off. I mentioned earlier that you have to be careful when you're shutting DX units off that they're set up to come back on again in the case of failure.
Oh, yeah.
Now, there's a control system called Icon Controls that Liebert supports that allows you to network the units together, so if one dies, the other one comes to life. And that's a fairly good system. There's also this issue of backflow. Once you shut one down, you should have flapper valves underneath it or on top of it, depending on how you've configured it, that shut. Just gravity, passive kinds of one-way valves, backflow prevention louvers that allow the system to fully shut. So in this case, VFDs was something the customer wanted to do. They were trying to make an argument for getting those DX units out of there and adding VFD-based systems in. And nowadays, this VFD does not mean chilled water because Liebert and others, APC and others, are now building variable speed, direct expansion kinds of cooling units. So you can replace, you can't always adapt the DX unit with a VFD. You can do a little of that, but only if you know what you're doing. I saw a presentation in AFCOM, and BIC has done that. BIC Group has gone in and put a few VFDs on DX units. But in order to make sure that they were going to work right, they had to take the DX unit, put it in their lab, and study it, engineer a solution to fit it because they weren't built to do it. But certainly new units, Liebert would clearly sell you a new unit that supports it, and it may be worth it for you to do it. So in this case, moving to DX-based units with VFDs allow you to get that RTI to be matched. In this case, provided for them some upside cooling capacity, and should increase the COP up to around 3 or 4. Again, it's important to measure that yourself, even after the systems are delivered, to keep a handle on what the energy consumption of your cooling system is. Okay? And, of course, modeling helps you understand that. So what we did in this case, this is a case we ran where we dropped the fans to 80%, which you can do in straight DX units. You can take them down 20% without much trouble. And so we dropped it down here to 32,000 from 39.5. And kept the temperature constant here in this case. We assumed the COP was going to be better. That 3.0 was not a measurement. That's an assumption, and based on the new unit. And RTI, therefore, came up to 70%. RCI still RCI high. Yeah, RCI low is still too cold. Now, in the case here, the reason that RCI actually dropped is you see in this category we also did some containment. Okay, we contained it and we put in new DX units running at 80%. Now, this is not unusual, right, Liz? I mean, what's happening here is my RCI actually dropped due to containment.
Right.
And the reason that's true is you're getting more uniform cold than you were before.
That's right. Less mixing of any, exhaust fumes, any exhaust air in with any of the supply air. So
that's right. Yeah. It's actually a good thing. What it's telling us here is we're getting more uniform distribution, and I'll show you in a moment. In fact, we are.
Uniform distribution, but of air that's still too cold.
That's correct. Of air that is still too cold. But it opens the door to turning up, of course, the temperature. You can see the PUE went up here. Now we're at 168, and the estimated savings per year to be 29%, about $74,000. At $74,000 a year, you can pay back a crack pretty quickly. So can we drive up air supply temp? And the answer is yes. Of course, I drove it here I drove it to 70 degrees just to see what would happen. Easy enough to do in CFD. You just wiggle parameters, right? You go back to the crack unit, set the leaving air supply temps to be higher, and up it goes. Now, I did assume here my PUE increased. I assumed my COP increased because I used that relationship of 3.5%, which is a fair place to start. These COP calculations will get more refined over time. We will continue to add more fidelity into the prediction model, but for now it's hand calculations are fair to give you an idea of where you are and where you might be. And here you can see savings of $81,000 a year by both raising supply temp, going to 80% airflow in this case, and containing. Containing doesn't have to be expensive. The curtains work fine, and they're movable, and you can change them. So we are seeing no rack high temps here. You see we brought our RCI low up here, so we're 100% now. So this is almost ideal. One question you could ask, you see RTI sitting there at 70%. A question you could ask is, Can we squeeze a little more out of it? Can we drop our 32,000 down a little bit more and still get away with uniform temperatures on our inlets within spec? And you can do that through modeling. Try it out and see.
Mm-hmm.
So here is the model fully contained at 70 degrees. I haven't yet dropped down, I don't think. Let's take a look at my summary report. I think we're running here still at 32,000. Yep.
Mm-hmm.
So this is the case, Liz, that is running at 20% down or 80% of max. I've got my RTIs there.
Mm-hmm.
And if you take a look at the thermal maps on this, they're nice and uniform. I mean,
Mm-hmm.
they look quite good.
Typical of any if contained.
That's right. Yeah. Now you see there is a corner right there that's a little bit warm. That could be that I didn't have my containment absolutely tight, which is actually a pretty fair representation of the real world.
Right. Right.
The other point about it, Liz, is it's right on an edge anyway. That's probably not going to bother a server. And furthermore, it's at the top. So, you know, what you would do there is just keep your servers away from the top.
Yeah, or just place equipment there that's not going to have high demands.
That's correct. Again, these tools are guides. They're not meant to be an absolute indicator of what's going on. It's not a, what would you say, Liz? It's not a, it's a guide, right?
Yeah. Yeah, it is. It's definitely a guide. Yeah.
It gives you the opportunity to understand the effects of parameter change on your model and see
changes. That's right.
Yeah, and see what effect it has. It gives you broad guidance into the direction you need to go.
Right.
It's
not true of all CFD. I mean,
it is true of all CFD.
CoolSim,
it's true of
all CFD.
Well, yes, it's true of modeling, right?
Modeling in general.
eQuest or any of the others as well is the same way. They are general indicators of which way a design is going to go based on a parameter set.
Right,
and
exactly.
They're not absolute value calculators. By the way, neither are calculators, are they? They're series expansions, right?
Yeah.
But many people, and I just want to stress this point, many people think these tools are all absolute value indicators, and they're not. They're used as guides to understand, should I move to the left or should I move to the right?
That's
What's
right. That's
the
exactly
general trend in which I should move in order to optimize something? So you can see here that, of course, it's leaking much less. We do have a little leakage going on here, of course, because A, curtains do leak, all barriers do leak, and B, my supply is greater than my requirement through those racks, and so you know you've got to account for the excess. The excess mass flow has to get back somehow.
Somewhere has to get back somewhere, right? Somehow.
Okay. So in the last case, what we did here is we dropped the fans down 37%. You see the RTI now went to 90%. Pretty good, but look what happened to the racks. And this means that we've just about got to the optimization point, that we're running at 70 degrees of cold air supply. We've got few racks in trouble, just a little bit. And by the way, we're calculating, of course, our calculations are quite conservative for this, as you know, Liz. So not too bad. We're saving 100 grand a year in costs. Some of that's coming from fans. You see the fan power is much lower. Fan power, if you remember, is a cubic relationship. So as you drop fan power down, the amount of energy saved goes up as a cube of the RPM. And so we're able to get about 40% out of this small data center. I mean, this data center is 1,600 square feet, 144 kW. It's not a big one. And we're able to pull $100,000 a year out of it in terms of electricity cost at 8 cents an hour, assuming 8 cents an hour, by doing some modest things here. In terms of cost, even if we replaced all 4 units, you know, at $100,000 a unit, it's 400 grand. And of course, you would want to put some containment in place. So the payback here is going to be less than 5 years, even if you replace them all. And I don't think you would replace them all. Furthermore, I'm not sure that it would cost 100 grand a piece. So here's the final run here. This is with everything in place. And let me just show you those rack inlets, Liz, so you can see where we're having. It's going to show up. I know you know where it's going to be. I mean, you and I get to the point where we can tell where the leaks are going to be. They're always in the same place. It's corners. So
and
again,
that's just from air circulating.
That's correct.
Circulating back around.
Yep. These are contained. It's probably a leak in my baffle, a little bit of a leak right there.
Yeah, well, that would have to be through a leak in the baffle.
Yep. And you'll see here on the return side, well, let's do supply side. On the supply side, you'll see much fewer path lines because now we're matching pretty well. We're matching demand versus demand versus supply are matched pretty well, so you get a nice even distribution and very few path lines coming back. So the room's in balance. By the way, the room will be quieter. And because
but those
this
few places, those few I see over on the right there where you can see some air coming from the cold aisle just going directly through the baffles and back into the crack. I mean, you're always going to, a couple of places like that where you're always going to see some of that.
Yes.
When you have excess air and, it's,
It has to, yes.
Yeah.
The other thing I wanted to point out here is I told you earlier, I mentioned earlier, I like hot aisle better. And the reason I like hot aisle better is because people do get into this environment and have to work in this environment. And if you take a look at the temperature in this environment due to the cold aisle and the 70-degree supply, you'll see here it gets kind of warm. So you see the aisles here that you operate in to repair equipment or to be in the room are pretty warm, running up into the 90-degree range, which makes perfect sense because if I'm supplying at 70 and I've got a 20-degree delta across this equipment, I'm going to be standing in 90-degree. At 6 feet, it's going to be 90 degrees. So that's okay from a design point of view. Sometimes the human component, the human element enters into these things, and people get very nervous about the fact that they're in a data center that's 90 degrees. You need to remember they're standing in the hot aisle, so that's why, but still it does make people a little bit nervous. I therefore tend to favor the alternative, which is, of course, the hot aisle contained. Yep. Okay, so that's it for today. I wanted to do a quick overview of some of these key parameters, how to get your hands around them. We reviewed coefficient of performance, which is very highly correlated to PUE. It is really the dominant characteristic of PUE. And again, it is simply understanding how much energy is going to your cooling system compared to the IT load in the room. Those are the two things you want to measure. Those are the two dominant energy components in your room, the cooling and the IT load. Make a ratio of those two things. Find out how to measure it. Again, if it's a DX unit, use current probes. Your electrician will know how to do that. He'll give you current readings. You can very easily, therefore, just calculate what the power consumption is. If you're not familiar with those equations, I can supply them for you. Send me an email. Or look them up on a wiki. Look them up on Google. The other thing is, what is the ratio of your airflow in the room? You want to try to ensure that it's fairly close. If it's not, then you're going to run into other problems like cooling off your return airflows and therefore getting poor heat transfer out of your heat exchangers. And you're also going to be spending a lot of money creating airflow that you don't need. And that's expensive because the airflow fan is a power consumer. And by the way, it's a thermal load in the room. So you really pay for fans twice. Once to blow the air to create the kinetic energy, and then the kinetic energy turns into heat, which you then have to dump. So it does hurt you twice. And then, of course, there's RCI, which is related to air supply temperature and specifically how that manifests itself on the fronts of racks. And there you need a CFD tool to understand how your changes are going to affect what goes on in the room. Of course, we are a supplier of CoolSim, which does this kind of work, and very cost-effective solution, by the way. So optimizing these parameters in some kind of iterative process allows you to understand where you need to go, what your direction ought to be, and gives you a path to the future for a more energy-efficient environment. And, of course, trade-offs do have to be made between volume of air supply temperature, and controlling that air. So this was a presentation I did, Liz, recently at the AFCOM show in Las Vegas. And it got some fairly good reviews. I thought I'd review it here today. I know my audience is quite varied in this seminar and webinar that I do, and I hope that it was of sufficient depth to give you some direction. And please provide feedback to us about what you thought of it, what you think the level is or ought to be, how much more depth we ought to provide. And at this point, Jennifer, I'll turn it back over to you, and we'll take questions from the audience if there are any.
Sure. Yep, we do have a couple. First of all, will the presentation be available to me, or should I be taking a lot of notes?
Oh, I'm sorry, I could have answered that earlier. I record all of these presentations and put them on the website. Under News and Events, there's a whole series of links for presentations we've done in the past, and I'll take this one and have it probably there, hopefully by tomorrow or at least by Monday.
Excellent. Okay, we have found that most servers nowadays move about 75 CFM per kilowatt, or about 50 degrees delta T. How does that affect your strategy?
Well, ours would be conservative compared to that. It makes the whole thing worse in the sense that you're going to have way too much airflow typically, right? I assumed 156. I assumed a delta T of 20. But if your delta T is 50 and you only need 75, then your cooling airflow, your cold air flow rate or supply flow rate has to come down that much more in order to match it.
You basically need a bigger temperature drop across the cracks.
That's correct.
The airflow balance.
That's correct.
It's just a matter of balancing the combination of airflow and delta T.
It doesn't affect the strategy at all. The strategy is the same. It just makes the challenge a little greater, if you know what I mean, to try to match that. And you will want to make sure that your calculation that you're doing, in this case 75 CFM per kW, is the same for all servers, because that's a low number, and I do know that they're running in that direction. So I wouldn't use probably 75 for everything. I would use a number in the range of 100 or 120 to get your calculation. Be a little conservative.
And then this is just kind of a follow-on, that the strategy being put forward in the webinar is based on 20 degrees Fahrenheit delta T.
Yeah.
And the comment was that's not what is currently made servers produce, except when incoming air is too high. And then, of course, leading back to should the strategy change with typical delta T?
No, the strategy is the same. No, the strategy is exactly the same. It's just I was being conservative. I assumed 156 with a delta T of 20. I could repeat the entire presentation with a CFM of 75 per kW and a delta T of 50. No, it doesn't matter. The methodology is exactly the same. The strategy is exactly the same. It's just
the numbers are just a little different.
The numbers are just a little different. Yes.
A little different, yeah.
Yep. But the methodology exactly the same.
Okay. I had another one. Can the software handle in-row or rack cooling?
Yes, so yes, yeah, the software can handle all of the things you normally run into. So in-row cooling, overhead cooling, yeah, you know.
Upflow, downflow.
Upflow, downflow, yeah. So the answer is yes.
That is all I had for questions.
All right.
Paul, I'm thinking maybe it would be a good idea for us to, do another webinar sometime where we look at some of those newer servers that have high temperature, that allow for large temperature rises across them, and just do another assessment. It might be a good opportunity for an upcoming webinar.
Yeah. Yep.
To look at some of the newer equipment.
I can certainly raise them, no problem at all.
Mm-hmm.
Okay. Is that it, Jen?
I believe so. So I guess we'll wrap up. We've got just about 3 o'clock Eastern Time showing. So on behalf of Carl, Liz, and myself, thank you for joining us today online, and we look forward. We'll be hosting more presentations in the future this year, so please feel free, as Paul has showed you, for either more information or if this is something that you're interested in taking a closer look at, please feel free to reach out to us, and we'd love to work with you. Thanks again, everybody, and have a great day.